Hello, everyone. My name is Felix Zitsky. I'm at the Institute for Quantum Computing at the University of Waterloo and Perimeter Institute. And this is my extended talk for the Beyond IID 8 conference starting next week on November 9. I want to tell you about my paper, Error Thresholds for Arbitrary Pauli Noise, that I've written together with Johannes Balsch at the University of Cambridge, that you can find on the archive. And in our paper, we discussed the quantum capacity of the quantum channel. And in order to motivate that topic, I want to first talk a little bit about general channel coding problems in information theory. So these problems are very fundamental because many communication tasks can be formalized as a channel coding problem. And in all of these problems, you have a group of senders that tries to send information through a group of receivers using a channel that connects them. And I want to be completely arbitrary here. So the senders, the channel, and the receivers could all be either classical systems or maybe quantum or some kind of hybrid situation between classical and quantum. So we can imagine that we want to send, for example, classic information through a quantum channel. Okay. And in all of these problems, the central notion is that of a capacity of a channel. Capacity is a quantity that tries to capture the information processing capabilities of the channel. And then the goal in information theory is to derive a coding theorem for this capacity, which means that we want to find an expression for the capacity that we can compute. And these expressions will usually be given as an optimization over certain entropic quantities. The best example and the first example of this is that of a classical point-to-point channel, which was discussed by Shannon in his landmark paper from 1948. And in a classical point-to-point channel, we have a single sender and a single receiver that are connected by a classical channel. And the goal for the sender is to transmit information to the receiver. And in order to do so, they agree on some codebook, and the sender draws a message from the codebook. And in order to transmit it through the channel, the sender encodes this message in the input alphabet of the channel, which now means that you have some sequence of symbols of length n. And each symbol in this sequence is transmitted by the channel to Bob. We assume that the channel acts in the same way on each of these symbols. And so now this input sequence xn will be mapped to an output sequence yn that the receiver now has. And then the receiver can try to decode the message in order to infer the original message that the sender wanted to send. And of course, the error in all of this is the probability that this decoded message m prime is not equal to the original message m that the sender wanted to send. And the capacity is now the largest number of bits per channel use that the sender can send through the channel, so that the error probability of wrongly decoding the message goes to 0 in the limit n to infinity, where n is the number of channels that they use. And now Shannon formalized this problem and then solved it and proved his famous noisy channel coding theorem, which tells us that the capacity of a classical channel is equal to the so-called mutual information of the channel. How do we compute this mutual information? We take a random variable x that represents the input to the channel, and we have a certain probability distribution px on this random variable. Now the channel acts on this random variable and maps it to an output random variable y, which corresponds to the receiver. And then we measure the mutual information between the random variable x and y. The mutual information is defined in the usual way in the lower left corner here. And Shannon's noisy channel coding theorem is beautifully simple, and it solves this problem of point-to-point classical communication. And as a result, this problem in information theory is extremely well understood. First of all, Shannon's formula is a so-called single-letter formula, which means that in order to evaluate the mutual information that is equal to the capacity, you only need to look at the output statistics of one copy of the channel. So in particular, this means that the optimization problem is bounded. This is good news. But it's not just any optimization problem, it belongs to a nice class of optimization problems called geometric programs, which is a certain type of convex program. And that means that we have a nice duality theory. For example, in order of, instead of solving the maximization problem for the capacity, we can convert this to a dual program, which is a minimization problem. And then result called strong duality tells us that the values of both of these problems will be equal. We can also efficiently solve this problem. We can efficiently compute the capacity of a classical channel. This is the so-called Arimoto-Blahoud algorithm. And it tells us that we can compute the capacity in time polynomial in the sizes of the alphabets of the channel, up to logarithmic terms. And last but not least, we not only know how to compute the capacity, we can also find actual codes, which means encoding and decoding procedures that achieve this capacity in the limit of many channel uses. So the best examples of these capacity achieving families of codes are low density parity check codes, turbo codes, or polar codes. So the point-to-point scenario in information theory is very well understood, but unfortunately, most tasks or most communication settings in information theory are not well understood. So for example, when you go to network information theory problems, which means that you add a sender or you add a receiver, then already this complicates the discussion quite a bit. And this is even more so the case if we add quantum resources to the problem. So for example, we now have a quantum channel and we still want to send classical information from one sender to the other, or we want to send quantum information. So in both these settings, when we have some kind of network information theory problem in front of us, or when we have quantum resources involved in the communication setting, we have a couple of complications that usually arise. So first of all, whatever algorithm we have to compute the capacity will now be much more complex, and it might be actually hard to solve this. What's worse is that we might leave this class of complex optimization problems, which are nice and kind of efficient to solve, and we have non-convex optimization problems that we need to solve, where we have no guarantee about convergence. And then kind of the worst case is that this bounded optimization problem turns into an unbounded optimization problem. I called the bounded optimization problem before single letter formulas. And in analogy, the unbounded optimization problems are so-called multi-letter formulas, and you will see one very soon. And so in this talk, what we want to focus on is the task of transmitting quantum information through a quantum channel. For this task, the relevant capacity quantity is the quantum capacity of a quantum channel. And we will see in the talk that we have these problems of non-convexity and unbounded optimization. And we will see that multipartite entanglement is kind of the reason why the optimization problem is unbounded. And so these are the main problems, but at the same time also the main objects of study that we have in our analysis. And we will try to come up with mathematical and numerical tools, in particular symmetries and certain optimization techniques, to study quantum capacity and try to find bounds on it. So this is the outline for the remainder of the talk. I will first define the quantum capacity in a bit more rigor. I will present the known coding theorem for the quantum capacity that we have, and the problems that come with it, in the sense that we don't really know how to solve it. In generality, which means that we have to focus on certain special cases. And in this talk, we will focus on a class of channels called Pauli channels, and we will look at the family of graph states that we want to use in order to study the Pauli channels. These graph states have certain decoherence properties, which I will explain in detail. And then this will give us a way of computing the quantum or bounds on the quantum capacity using these graph states. And then I will explain to you how we can use graph symmetries in order to speed up this computation and help us find these lower bounds on the quantum capacity. This I will then do in the main result section of this talk, where we will study the error thresholds of these Pauli channels using our methods. And then I will conclude with a summary and some open problems. Okay, let's do it. So what is a quantum channel? A quantum channel models noise in a quantum system. And there's two viewpoints that we can take. We can take the viewpoint of information theory, where we imagine we have two quantum systems that can communicate with each other through a quantum channel. But this quantum channel is noisy, so it kind of tries to disturb the information that we want to send from one party to the other. So we speak of a noisy communication link between quantum parties. There's another viewpoint from quantum error correction, where we can imagine we have some quantum device, a quantum computer in front of us, and we want to store and manipulate information, quantum information on this computer, but the environment tries to disturb the information. And so the quantum channel, a quantum channel is a way of modeling this environmental noise that our quantum device is subjected to. So we have these two pictures of a quantum channel, and then the quantum capacity tries to characterize the noise in the quantum channel in a certain sense. So in the information theory picture, the quantum capacity tells us how much quantum information can we send faithfully through the channel. In the error correction picture, the quantum capacity tells us how much quantum information can we protect against the noise that the environment exerts on the quantum device. Both pictures are, of course, equivalent to each other. It's just two different ways to look at it. I will focus more on the information theory picture. In order to describe this in a little more detail, we can imagine that we want to generate entanglement using a quantum channel. We know by work of Devetak that this is equivalent to sending quantum information through a channel. Okay, so the task is we have two parties, Alice and Bob. They're in separate labs, and the only connection between them is this quantum channel N. And their goal is, their goal is to generate entanglement between Alice and Bob through the channel. And what we can do is we can imagine that Alice first prepares a pure bipartite state in her lab. So this is the state psi here with, let's say, two qubits R and A. R is the reference system that will stay with Alice, and A is the channel qubit that Alice sends through the channel to Bob, so that Bob will end up with a system B. And now Alice and Bob share the state on R and B. And because of the noise of the channel, this state will now be mixed. So the initial pure state will be mapped to a mixed output state of the channel because of the channel noise. And now what Alice and Bob can do is they can share K independent identical copies of this initial state through the channel, so that they end up with K copies of this output state. And then from this output state, they can use entanglement distillation to try to distill EPR pairs. And kind of the more EPR pairs they distill, the more entanglement they have generated between them. And in these entanglement distillation protocols, what the allowed operations are local operations in Alice's lab and in Bob's lab, but they have to be independent of each other. And they can use forward classical communication. So Alice has a classical channel to Bob, and she can send him a classical message that may help him in the distillation process. And by the work of Devetak and Winter from 2005, we know that this is indeed possible. There are distillation protocols, and they distill EPR pairs at a rate equal to the coherent information of this initial state. What is the coherent information? We take Bob's half of the state on B and look at its von Neumann entropy. And then we subtract the joint entropy that is in the state on R and B. And this measures somehow how much correlation Alice and Bob can establish using this channel. But this is not everything they can do. Instead of preparing this initial state K times and preparing the same state K times, Alice could also start by preparing some more complicated multipartite state. So we again assume that Alice does this in her lab. She prepares a pure state, but this time there are, let's say, n A systems, and she has some weird multipartite pure state in her lab, which again consists of a system R that will stay with her, and these channel systems A1 through AN that she sends to Bob through the channel. The channel again acts on each system in the same way and independent of each other, so that they end up with a big multipartite state shared between them, where R is with Alice and the B I systems are with Bob now. This state again has some query information from R to B1 through Bn. And doing this, sharing this state now k times, we can again use the entanglement distillation protocols by Davidoff and Winter to try to distill EPR pairs using these big multipartite states. And the rate in these protocols will now be given by the normalized coherent information of this big initial multipartite state, which is this quantity here. So the psi n here is now this pure multipartite state that I started with, and half of which I share using the channel. And then I normalize by the number of channel uses. And why would I do this? The point is now that for certain channels and certain input states or quantum codes psi n, we can actually achieve a larger coherent information than if we only use a single copy to share a state, and then we do this many times. Okay, so this phenomenon is called superadditivity of coherent information. It was a breakthrough result in quantum information theory, first discovered by Shor and Small in '96, and then further discussed in a follow-up paper by DiVincenzo, Shor and Small in '98. And it tells us that if we use the channel only once, there's a certain coherent information we can achieve by choosing the best input state, but we might beat that by choosing a big multipartite entangled state, sharing the state using many copies of the channel, and then normalizing the resulting coherent information. And so this is now this now leads to the quantum capacity of the quantum channel, which is formally defined as the largest rate at which EPR pairs can be generated using a channel, such that the error vanishes asymptotically. I haven't defined the error because I want to stay kind of like informal here. And then we have a coding theorem for the quantum capacity now, which was proved by Lloyd, Shor, Davidoff around the turn of the century, that tells us that the quantum capacity is actually equal to the largest normalized coherent information that we can achieve by distributing a large multipartite entangled state using a channel in the way that I showed you just before. Okay, so the quantum capacity theorem tells us we take a large multipartite state, we send half of it through n uses of the channel. Then for a fixed n, we take the best input state, we take the side that gives us the maximal coherent information. But now we actually look at all number of channel uses and we check where do we get the largest coherent information. And this is now where the problems come in, because of the superadditivity effect that I showed you before for certain channels and states, we don't actually know where this supremum, this outer supremum here over integers actually happens. So in a sense, you need to check all of them. And this is of course unbounded because the integers are unbounded. So this leads us to an unbounded optimization problem. And this is exactly this kind of multi-letter coding theorem or multi-letter expression for capacity that I alluded to before. And we also know that there's some very pathological behavior for certain channels. So there are channels where you actually never know where to stop checking in a way. There's another problem that even if you fix the number of channel uses that you want to check, so you make the optimization problem bounded by saying, I only want to look at 5 channel uses, for example. But even then, the resulting coherent information on these fixed number of channel uses is non-concave in the input state, which means that from an optimization point of view, when you try to maximize a quantity that is not concave, this is a problem because whenever you find some local maximum, you don't know if it's global or not. And we are interested in global maxima here. So these are two very big problems when you actually try to compute the quantum capacity. And now we need to find ways to work around this. And the first the first observation is that the superadditivity of coherent information comes about from multipartite entanglement in its initial code state. And we know for mathematical reasons, it's hard to describe multipartite entanglement, because when you look at Hilbert spaces of growing, like if you look at the Hilbert space of n qubits, then the dimension of the underlying Hilbert space is is exponential in the number of qubits, because the dimensions of the individual Hilbert spaces multiply in the tensor product. So as the n, the number of qubits that you look at, is growing, it becomes harder and harder to characterize multipartite entanglement because of the exponential scaling of the Hilbert space dimension. And furthermore, even if we fix the n, and so we have like a bound optimization problem, then the objective function, this Coherent information here on the inside of the optimization problem, is still non-concave and hard to optimize. So we need ways to deal with these problems. One possible computational ansatz that I explored, for example, in an earlier paper with Johannes, is that you can try to restrict the Hilbert space of possible quantum states to a subspace with polynomial dimension in n, in the hope that this polynomial subspace will still have a sufficiently rich entanglement structure of the states that live in this subspace. So this is an old idea from Condon's meta theory, which has been used to a lot of success. And tensor networks are one way to do this. Another way to do this is the more recent advance of quantum neural network states. And this is the approach that I explored with Johannes in this earlier paper. So this is more on the computational side of things. There's also a possible mathematical ansatz, where for specific quantum channels and specific codes, you can try to leverage symmetries in the code in order to compute the Coherent information and kind of bring this the number of degrees of freedom down from exponential to polynomial. One way to do this is to use permutation invariance, which was, for example, used in a paper by Card and Rennes. And what we will focus here on in this talk is symmetries coming from a graph. Okay, so this leads me to the second part of the talk. We now want to try this ansatz to leverage symmetries. And for this purpose, we restrict our focus to a subclass of channels called Pauli channels, which are channels in which one of the Pauli matrices acts as an error on the channel qubit with a certain probability. So we have our Pauli matrices X, Y, Z, and we have a probability distribution P0, P1, P2, P3. And we assume that with probability P0, nothing happens to the qubit. With probability P1, there's an X error happening on the qubit. With probability P2 and P3, there's a Y or a Z error happening. So this is a very nice error model, but it's very fundamental. There are very important examples in this class of channels. For example, depolarizing noise, in which each of the Pauli errors happens with the same probability P/3, is in this class. But also, for example, the BB84 channel, which models the noise in the BB84 quantum key distribution protocol, is also an example of this class of channels. And the motivation to look at this, you can take from quantum error correction, where we know that in order to correct arbitrary unitary errors, it's actually enough to be able to correct X, Y, and Z errors. So you're allowed to discretize the unitary error group into X, Y, and Z errors. And what we will do in particular is we will look at certain one-parameter families of these Pauli channels. So what we do is we fix some triple P1, P2, P3, which are kind of like the probabilities of X, Y, and Z happening. And then we say we have a certain noise level X, so that with probability 1 minus X, nothing happens to the qubit. And then as the X increases, we mix in this P1, P2, P3 probability of an X, Y, or Z error happening. And then for this one parameter family of channels, we can now ask, what is the largest X such that the channel still has capacity? And we call this the threshold of this channel family. So the threshold is defined as a supremum over all x such that the quantum capacity is still positive. And in our two pictures, quantum information transmission and quantum error correction, a positive quantum capacity means in the information transmission picture that faithful quantum communication is possible at a positive rate. And in the error correction picture, it means that if the quantum capacity is positive, then it means that there exists an error correction code that protects the information from the environmental noise at a certain rate. Okay, so we have this family of channels called Pauli channels. And what we are interested in now is when we have tensor powers of this channel acting on some multipartite state. And what you observe is when you take tensor powers of a Pauli channel, what you will get is a channel where the error operators or cross operators are so-called n-qubit Pauli operators. So they are tensor products of single qubit Paulis together with some phase. And we have this probability distribution PIN, which comes from the initial distribution that we have for each error. So we're effectively dealing with n-qubit Pauli operators when we look at these tensor channels. And so this now suggests to take as a quantum code on which the channel acts a state that behaves in a certain way when Pauli errors from this n-qubit Pauli group act on it. And this family of states are the so-called stabilizer states. So stabilizer states are defined as states that are stabilized by k pairwise commuting stabilizer generators, which are called SI here. This was invented, the stabilizer formalism was invented by Daniel Gottesman in his PhD thesis in '97. It's a very rich theory about stabilizer states, stabilizer groups. This is a way to characterize multipartite entanglement. And I won't go into the details of the stabilizer formalism. What we want to look at is a certain subclass of stabilizer states that are defined in terms of a graph. So we take a simple undirected graph, gamma, with a vertex set V and an edge set E. So I've drawn a graph here with 6 vertices. And we now define stabilizers for each vertex of the graph where we put an X operator on a vertex and a Z operator on all adjacent vertices. So the adjacent vertices to a vertex are the ones that are connected by an edge. So for example, in the example graph here on the right-hand side, I have drawn the stabilizer generators corresponding to the second and the fourth qubit or vertex. So here for the second vertex, we see we have an X operator on the second qubit and Z operators on the first and third qubit. If we do this for the fourth vertex or qubit, we have an X operator on the fourth qubit and Z operators on the third, fifth, and sixth qubit. And now we define the graph state as the unique pure state that is stabilized by these K generators, one for each vertex. So for this graph of 6 vertices, we have 6 stabilizer generators. Okay, this subclass of stabilizer states called graph states is a very important subclass because of the fact that every stabilizer state is locally unitary equivalent to a graph state. Which means if I take an arbitrary stabilizer state psi k on k qubits, there exists a graph and some local unitaries u1 through uk, such that acting on the stabilizer state with these local unitaries, I get the graph state. So in every local unitary orbit of a stabilizer state is a graph state. And there are some important examples of stabilizer states, and then using this theorem, we can look at the corresponding graph states, which are local unitary equivalent. So one of the most important quantum codes is the repetition code, where you take the computational basis, the Z basis in this case, and you just replicate it. So you create an equal superposition of the all 0 state and the all 1 state. And the graph state that's local unitary equivalent to this repetition code or GHZ state, as it's called in physics, is the star graph. So a star graph is a graph where you have one root vertex, and then all of the other vertices are just connected with a single edge to this root vertex. And in all of the diagrams that will follow, since we want to distinguish between qubits that go into the channel and reference qubits, to say with Alice, we need to distinguish them in a graph. And so the hollow circles will always label reference qubits, and the full circles will always label system qubits. So for example, here in the star graph, we could imagine that this qubit here is the reference qubit, but actually it doesn't matter which of the reference qubits, which of the qubits you choose as the reference qubits. So this is in a way permutation symmetric here, even though it doesn't look like it. Another very important example of a quantum code is the so-called Shor code, which you get by concatenating a stabilizer code, which you get by concatenating a repetition code of Z type with a repetition code of X type. What do I mean by this? Here, this is a Z type repetition code. The X type repetition code is just with the plus minus basis instead of the 0-1 basis. And then for a cat code or a Shor code, I first take a Z type code, and then I use that as the code states to create the plus and minus states. And then this is the outer X type repetition code. And there's a graph state that's local unitary equivalent to Shor's code. And this is the graph that I've written down here, where again, this hollow circle here is the reference qubit. And this is a code on 9 qubits with a 10th reference qubit. Okay, so we know what Pauli channels are, we know what graph states are, and we know that we can express certain quantum codes as graph states. And now we want to see what happens when a Pauli channel acts on a graph state. So remember, our goal is to kind of find bounds on the quantum capacity of a channel, which is given by these two maximizations or suprema of the query information. What this tells us mathematically is that since it's two maxima, if we can find a particular example of an input state psi n and a particular n such that the right hand side here is positive, then we will find a lower bound to the quantum capacity, and therefore we will kind of like know that the threshold needs to be further out. And so in our talk, in our paper, we choose graph states as the input states. So these psi n's for us will be graph states. And the goal is to compute the query information of this graph state where the channel acts on some of the qubits. So we need to compute the tensor action of a Pauli channel on this graph state. And now the crucial observation is, and this was done in a paper by Hein et al., references on the next slide. The crucial observation is that a graph state translates any Pauli error into a Z-type error. What do I mean by that? I have three types of Pauli errors, Z, X, and Y. The Z error, if I have, for example, a Z error acting on a second qubit, there's nothing to do. This is already of Z type. Now, if I have an X error acting on a second qubit, I can remember that my graph state is defined as the stabilizer state, where the stabilizer generators are the stabilizer operators with an X operator on the vertex and Z operators on the adjacent vertices. So if I have an X operator acting on a second vertex, and this is the error that's occurring, I can imagine that I have the stabilizer here sitting, because the state is invariant on the stabilizer by definition, so that the X error on the second qubit annihilates the X operator that's sitting on the stabilizer. And what I'm left with is the two Z errors that sit on the adjacent vertices. So now you see this X error acting on the second qubit has been translated into a Z error acting in the neighborhood on the adjacent qubits. If I want to handle Y errors, I just have to write a Y error as a product of X and Z errors, modulo phase, which is not important for us. So I can imagine I first have an X error acting on a second qubit, which gives me these two Z errors on 1 and 3. And then I have another Z error acting on the second qubit, which gives me a Z on the second qubit. so that the y arrow acting on a second qubit has now been translated into z arrows acting on the second qubit and on the adjacent vertices. And you can see graphically that the decoherence rule for y arrows is just combining the decoherence rules for z arrows and x arrows. You see this graphically here quite nicely. So mathematically, this is another way of writing down what I've just said. So z arrows just stay z arrows. X arrows are translated, when they act on a graph state, they're translated into z arrows on the neighborhood of that vertex, and y arrows are translated into z arrows acting on that vertex and the neighborhood. And what I can follow from these decoherence rules is that when I have a graph state and a Pauli channel acts on some qubits of that graph state, then the output state will be diagonal in a certain basis called the graph state basis, which I obtain from considering all z translates of the graph state. By z translate, I mean I take some subset of vertices. I have z arrows acting on the subset, on each vertex in that subset, and then that gives me a new state. So I have 2 to the n states that I can get like that, one for each subset of the vertex set. And so this constitutes a basis for my n qubit space, which is called the graph state basis. And my output state of the Pauli channel acting on that graph state is diagonal in that basis by the decoherence rules that I showed you. And we will have certain coefficients lambda, one for each subset, one for each basis vector, which is labeled by subsets of the vertex set. And so now the coherent information is a function of the eigenvalues of a state. So, and this is a diagonal decomposition. So the lambda u's are the eigenvalues of the output state. So in order to compute the coherent information, what I need to do is I need to determine these coefficients lambda u for all subset vertices u. Let's do an example of this. Let's assume that we have a star graph on 4 vertices, one of which is a reference qubit, and 1, 2, 3 are channel qubits, which are affected by noise by the channel. And remember, I have this formula, so I need to kind of determine these lambda u coefficients for all the subsets u of the vertex set. And let's take as an example the subset 1, 2. So I want to look at, I want to compute the coefficient lambda u, where u is the first and the second vertex. And what I need to do is I need to kind of look at all Pauli errors acting on the 3 channel qubits 1, 2, 3 that lead to this subset 1, 2 when I use these decoherence rules. And then you can convince yourself that there are 4 Pauli errors that lead to this subset, that lead to z operators sitting on these vertices. So first of all, we can have a z1 and acting on the first a z operator acting on the first vertex, a z operator acting on the second vertex, which means that I have z's here, an identity on the third vertex, and the channel gives me the probabilities with which these errors occur, and if I now tally up the contributions, I get this probability for this error happening. If I can also achieve the subset u by acting on the second vertex with a y operator, because we know a y operator always activates the vertex itself and every adjacent vertex. So if I act with a y here, I activate this vertex and this vertex. So again, 1, 2, and I get a certain contribution according to the Pauli channel probabilities. And then I can do the same with a z arrow acting on the second vertex and an x arrow acting on the third vertex, because we know x arrows activate all adjacent vertices. So if I act here with an x, I activate the first one, and I activate the second one with a z operator acting there. So I have this operator, I get a certain contribution, I sum them up. And the fourth one is that kind of like combining the 3 previous ones. So I act with a z operator on the first one, a y operator on the second one, which activates this and deactivates this, because applying Z twice is just identity. And then I activate this again with an X on the third operator, on third qubit. I get a certain contribution, and then I sum this up to get the lambda coefficient. And in theory, I can just, for a given graph and number of vertices, I can just do this for each lambda u, for each subset. The problem of that being, of course, that this scales exponentially in the number of qubits, because I have exponentially many subsets of a set of size n. So the idea is now to kind of remedy this problem and use graph symmetries so that we don't have to compute all of these lambda coefficients. And to see how this works, let's revisit our example from before. We have again the star graph and 4 vertices, 1, 2, 3, 4. We want to look at the subset U that consists of the first and the second vertex. But now observe that our graph has a graph automorphism given by exchanging the second and the third vertex. So a graph automorphism is a permutation of the vertices of a graph such that the incidences are preserved. So the edges are, what was an edge before will be an edge later. And if I take these operators that all lead to the U subset that I want to look at, the 1, 2 subset here, and I apply this graph automorphism to all of these operators, I get a new set of operators. But since I have an IID channel, meaning that the channel acts the same on each qubit, these will have the same probabilities as before. So the subset U that I was looking at in the first step, the 1, 2 subset, by the automorphism is mapped into the 1, 3 subset because it switched 2 and 3. But then it has the same coefficient as the 1, 2 subset. Because of the fact that I have an IID channel, it acts the same way on each vertex. And I just need to kind of permute my operators. And so this is something I can exploit now. In a little more detail, what we want to look at is the so-called two-colored graph automorphism group of a graph. Two-colored because we have to distinguish between system qubits and reference qubits. And what we do mathematically in order to really implement this in a numerical way is that we have certain n-qubit Pauli operators acting on the graph state. And what we do is we identify these operators with quaternary strings. So we replace identity by 0, x by 1, y by 2, and z by 3. So for example, an arrow operator z1, x3, y4, so z acting on the first vertex, x acting on the third vertex, and y acting on the fourth vertex, by this isomorphism is mapped to the string 3, 0, 1, 2. And on the other hand, we have now these decoherence rules that for a given arrow operator give us a certain subset on which the z operators act. And these we identify with binary strings in the obvious way. So if there is a z operator sitting on that vertex, we take a 1, otherwise we take a 0. So for example, for the 2, 3 subset, this will translate into the string 0, 1, 1, 0. So the 1 in the second and third position, meaning that I have z operators acting on the second and third vertex. And these are now two sets, the set of quaternary strings of length n and the set of binary strings of length n. And my automorphism group acts on both of these sets. So this is a group action. And the important observation is now that these two actions are related to each other. They're so-called homomorphic actions, which means that basically, if I first permute my arrow operators with the automorphism group, and then I do the decoherence rules and map it to a binary string, it's the same as first mapping it to the binary string and then permuting it. So in mathematical terms, the decoherence rules induce a G equivariant surjective map theta from the set of quaternary strings to the set of binary strings. And I've written down an example here the example is with these two strings that I wrote down before. So I have 4 qubits, and let's take this graph, for example. And I have the error operator Z1, X3, Y4. So the Z operator acts on the first vertex, so it activates the first vertex. I then act with the X operator on the third vertex, and X operators act all the adjacent vertices. So I activate the fourth vertex, and I deactivate the first vertex. So this is the dashed line here. And then finally, I act with the Y operator on the fourth vertex, which activates the adjacent vertices, 2 and 3, and it deactivates the fourth vertex, which was activated before. So this is just a graphical depiction of the fact that the error operator Z1, X3, Y4 is mapped to the string 0, 1, 1, 0, which corresponds to this picture here. And the fact that I have homomorphic group actions means that if I apply a graph automorphism, it doesn't matter whether I do it before or afterwards. So here in slightly more detail, how we use this is, so we have these two sets, the quaternary strings Q, the binary strings B, both of length n. I have my automorphism group G acting on both sets by permuting strings. And I have this G equivariant surjective map theta that is defined by the decoherence rules. And then the fact that I have a homomorphic group action or homomorphic group actions means that if I take a look at all the orbits that I get from acting with my group on the first set Q, then all of these orbits, like each of these orbits in Q, will be mapped into an orbit on the group action level B. So I have my quaternary strings, I have my binary strings. On both, I have a group action. I have my group action orbits here. I have my group action orbits here. And the homomorphicity of the group actions tells me that the orbits of the quaternary strings are completely mapped into some orbit of the binary strings. And this mapping does not happen in a weird way. It actually happens in a way that I have a uniform covering of my orbits in the binary strings. So this is mathematically, this is this statement, but really pictorially, it's easier to see that I have my binary string orbits here, and all of these orbits are completely mapped into one of them, and this mapping happens uniformly. Sorry. And so we can use this in order to compute these output states of a Pauli channel acting on graph states. Because what we can do now is we can take orbit representatives of the first group action on the quaternary strings. We then do the mapping. We see in what orbit am I mapping to. And I record this orbit. This will determine what lambda coefficient I'm talking about, because these U subsets, they label the orbits for the binary strings. And then I just do this mapping, and I try to keep track of the contributions and multiplicities that I get using this homomorphic group action result. And the cool thing about this procedure is that I can do this analytically, because I don't need to know the actual values of the Pi probabilities that define the Pauli channel. So I can just do this on an analytical level, and then I really get analytical expressions for these eigenvalues lambda u, and therefore I get analytical expressions for the coherent information. I can also do this. I haven't told you how to take the partial trace of this. There's a way to do this that respects these symmetry considerations, and let us do this efficiently. Using both results, I can then really write down an analytical expression for the coherent information of a Pauli channel acting on a graph state by exploiting the graph symmetries. And we want to use this now in order to study error thresholds for Pauli channels. And the way we do this is the following. So I told you before, we focus on this family of Pauli channels, and we look at them in this way of one parameter families that are characterized by this noise level X. So I take some probability distribution P1, P2, P3 for the X, Y, and Z type error. And then I have this noise level X with which I mix in this noise on the qubits. I fix this Pauli channel and I fix a certain graph state, let's say on n+1 qubits. And now I want to compute the current information of the Pauli channel acting on n of these n+1 qubits. One is always a reference qubit. And I told you that we have this algorithm to compute these lambda u coefficients. And we can do this analytically. So we can really do this with variables P0, P1, P2, P3. If I then take this particular form of these variables P0, P1, P2, P3, I actually now get a function of one single parameter x, which is the core information. And we prove in the paper that this function, the core information of the Pauli channel, depending on this x noise level, is actually non-increasing, which means that in order to find the threshold, I only need to find the first root of this function f. Okay? And we can do, since we have these analytical expressions, what we can do is we can actually kind of vary the initial P1, P2, P3 distribution that we have here so that we get now all the channels in the Pauli channel simplex, which is kind of spanned by the three probabilities. Okay? And so as we vary this initial distribution, we actually get a threshold surface because each channel, each one parameter channel family defined by Px is just some ray originating at the origin and pointing outwards, and it will hit 0 at some point, and this defines a surface. This is much better understood with a picture. So here is a picture. We first did this for the family of repetition codes, where we took the star graphs which correspond to repetition codes. We took star graphs of up to 60 channel qubits. And then we took channels with this noise level X and some initial distribution P1, P2, P3. So each of these one parameter families now corresponds to some ray originating at 0 and pointing outwards here. And then along this ray, at some point, the core information will hit 0, which will define the surface at this point. And if we vary over the P1, P2, P3, what we get is this kind of like triangular surface here in the Pauli channel simplex, which defines, like, we took the maximum for all star graphs that we looked at, and this gives us a surface. And now you see colors in the surface. What is this color? We have these, for this particular family of channel along a certain ray defined by P1, P2, P3, we have a certain threshold coming from the graph states, but we also have a certain threshold coming from the single letter information, which I get when I just maximize one copy of the channel. I take an input state on one qubit, and maximize the information, and I get a certain threshold. And we color the points on the surface depending on whether we have superadditivity or not. So if the color is, if this is positive here, if we have a color that's between yellow and blue, and like in the middle it's greenish, if we have a point colored in that color, this means that the graph state has a higher threshold than the single letter information, and therefore we have superadditivity, because the threshold is further out than if we had looked at the single letter information. And if the color, if we have a negative value, if the color is yellow, orange, reddish, then we don't have superadditivity, because that means that the threshold for the graph states is actually worse. It's further in than the threshold for the single letter information. And we see that the family of repetition codes gives us superadditivity in a large area of the Pauli channel simplex, in a large area of the surface threshold. So to relate this to previous results and works, this has been long known that repetition codes extend the threshold of certain Pauli channels. In particular, it was known that they extend the threshold of deporosing channel, and the threshold also for BB84 channels. And these special channels are marked with a black dot here. So these are kind of like these determined arrays that correspond to these channels. Although the BB84 channel is not actually a ray in our sense, because it has these quadratic terms in it. But the ray intersects the family of BB84 channels at this point. And we kind of recreate these results that, for example, for the deporosing channel, we have this green color here, which means that there is a repetition code that gives us a better threshold. In this case, it's the 5 repetition code. But because of the fact that we have analytical expressions for the Coulomb information that we can evaluate in a whole polychannel simplex simply by substituting values for the variables, we can actually test the superadditivity in the whole chip polychannel simplex. So for all of these points here, which correspond to the threshold for a specific family of channels, we can check, do I have superadditivity or not? And so we can make this analysis for all of these points, and we see that in these blue regions here, we have actually large areas where the repetition codes get better and better, because we get more and more superadditivity. We can also do this for the concatenated code family. So these are the short type codes where I take a Z type repetition code and then I concatenate with an X type repetition code. And it's been known by the work of Di Vincenzo, Shor, Smolin, that the 5 and 5 code is actually kind of like a very good one in this family. So we took the 5 and 5 code. The graph state that's LU equivalent, local unitary equivalent to the 5 and 5 code is this graph here, which looks a little daunting, but if you stare at it and compare it to the short code I showed you before, you can see that there's a construction that you can do, and we say in the paper how to do this. And then we again look at the threshold surface, and then we look at, we color the points according to whether I get superadditivity using the 5 and 5 code or not. So again, same color legend as before. If I have a green or blue color, I have superadditivity. The threshold is improved by the 5 and 5 code over the single letter threshold. If I have a red color, it's worse than the single letter threshold. And we again see that there's large parts where the 5 and 5 code indeed improves the threshold for these polychannels. Again, our work is the first one where we can do this for the whole polychannel simplex and not just individual channels, because of the way that we compute these things. We have this analytical expression that we can use substitution with. And we see that we again have large areas where we have superadditivity. If you allow me to switch back and forth between the first picture, you see how the areas slightly change and also the magnitude changes. So the repetition code is actually better if you have biased noise towards the Y and Z type errors, because it's bluer, and blue corresponds to large superadditivity. On the other hand, the 5 and 5 code does much better around the deporosing channel. So around this area here. And this reflects the fact that it is actually known that for up to 25 channel copies, the 5 and 5 code has the best threshold for deporosing channel. This is kind of proven, or to some extent proven. And we see that this actually also holds in the vicinity of the deporosing channel, which is quite nice to see with our method and our plots. And finally, we also played around with graphs that we wanted to look at, and we saw that there's actually an interesting new family of quantum codes based on tree graphs. Tree graphs are best defined pictorially by, you have it's graphs without any cycles. And what we looked at were tree graphs with 2 levels. So you can arrange the qubits in kind of like levels, and then we have like 2 levels that are connected to a root. In each case, one of them is again the reference qubit. And we actually saw that this code family of tree graphs with 2 levels with a certain configuration and vertex number is very competitive and actually kind of like comes very, very close to the threshold of the 5 and 5 code, which is known to be the best one, or thought to be the best one for up to 25 channel qubits. And you see this here in the plot. In contrast to the other plots, this is now a comparison between the family of tree graph codes and the 5 and 5 code. So again, if I have a blue color, it means that the threshold of the tree graphs is better than the 5 and 5 code. Yellow means it's the same, and red means it's worse than the 5 and 5 code. And we see here actually that around the depolarizing channel in this vicinity, the code performance is competitive. So it's yellow, it's roughly the same. It's actually better in for X-biased noise. So here we have green and blue colors, which means the threshold for the tree graphs is better than the one for the 5 and 5 code. But it's worse, for example, for Z-type noise and in this area here. But this is a new code family that was not really looked at in the context of quantum information transmission or quantum error correction, for that matter. And it will be interesting to see whether this family has some further nice properties with regards to error correction. Okay, so this brings me to the conclusion. So we try to employ symmetries in channel coding problems in order to get bounds on the quantum capacity. In particular, we used the graph state formalism and exploited their graph symmetries and tools from group theory to approximate the quantum capacity of Pauli channels, which are an interesting subclass of channels. And we were able to produce these nice pictures, which are hopefully kind of like convey what we're trying to do, like trying to see what are the error thresholds for these Pauli channels when you test them with graph states. And there are, of course, like a lot of open problems that we want to address in future work. One is, can we channelize these methods to handle more general quantum channels? Because Pauli channels are just a subset of quantum channels. We took a lot of tools from computational group theory to handle these homomorphic group actions and keeping track of these orbits and what they're mapped to. And there are some tools to do this computationally, but we did hit some bottlenecks in our studies. So we were wondering, can we improve these tools in order to increase the regime in which we can test these things? And the third one is this group theory framework and the framework of group actions and computational group theory is very powerful. It helped us come up with these analytical expressions for co-information, which is awesome. The question is, can we use these techniques in other contexts, in particular in quantum error correction, where you have want to analyze codes and decoding procedures, and you also want to look at thresholds, like the largest noise level that you can tolerate. And we think, or we hope that this framework that we kind of like introduced to quantum information theory in this paper will be helpful in studying quantum error correction. Okay, so this brings me to an end. I have included 3 QR codes. The first one is where you can download our paper from the archive. The second one you can use to download these slides that I used. And the third one links to my homepage where you can find contact information in case you want to send me an email and have some questions or suggestions for improvement, etc. And with this, I'd like to conclude and thank you for your attention.